To maximize the time, the floor time of the speaker here will begin about 30 seconds early. It gives the chair no greater pleasure than to invite back one of his own PhD students to give the colloquium. This is Mauricio Ayllon Unzueta. He grew up in Bolivia. He got his degree at Eastern Michigan University. He then went to the Swiss Federal Institute of Technology for his master's degree, and then came here as a graduate student and received his PhD in 2020. He worked on the high-flux neutron generator. He was sort of a lead graduate student there. We did a lot of great science. And then he grabbed a very interesting opportunity with Peru up at Morrisburg, where he designed and developed a neutron generator for mapping subsurface carbon, sort of a mobile platform for doing mapping of subsurface carbon under an RPE grant. He then has become a postdoctoral fellow at NASA in Goddard Space Flight Center. And he's going to talk to us today about planetary nuclear spectroscopy. We'll talk about neutron and gamma ray spectroscopy of planetary surfaces. It's going to, at the culmination of this, is going to be an incredibly fascinating talk. He's going to tell us about the Dragonfly mission to Titan that will hopefully launch in 2027, arrive at Titan in 2034. And you're going to see this really interesting. You're going to give us a simulation of the octocopter going around.
Yeah.
Good. Without further ado, Mauricio.
Right. So, thank you very much. It's great to be back in Berkeley. It's great to see old faces and new faces. So let me just get right into it. I'll talk about planetary nuclear spectroscopy. This is my more immediate group and some collaborators at Berkeley, Arun, that we're doing an experiment, and I'll talk about it a little bit later on. But as you can see, it's really a collaboration between organizations like NASA, Goddard, Johns Hopkins Applied Physics Lab. Before I begin, I'd like to remind you about nuclear technology and how it has far reaches into different fields. And you probably know all of this, and space exploration or space applications is not the exception. So here you can see the first and the only fission reactor that was flown by the US. It's the SNAP 10A. It was a NAC-cooled reactor that produced 500 watts of electrical power. And I believe it's still orbiting around it. It lasted for about 40 days or so. These are multi-nuclear batteries, or just so to speak. These are multi-emission radioisotope thermoelectric generators. And what they are is they're just big nuclear batteries that produce energy so they're returning 238 pellets that produce a heat differential. Through the Seebeck effect, you can get a differential in voltage as well. They can work with batteries, and they're everywhere in NASA missions. This is an example of the latest Mars rover, the Perseverance rover, the latest and greatest so far. And you can see the MMRTG right there. This is a simulation of X-ray deposition of an asteroid, asteroid Bennu, as a result of a 1 megaton nuclear detonation that is nearby. An asteroid Bennu is a near-Earth asteroid, so this is the only way so far that we know of how to deflect an asteroid of that size. And a lot of this work is being done, or most of this work is being done at Lawrence Livermore. And finally, what will be the focus of my thoughts is a planetary nuclear spectroscopy, which is a blanket term for a gamma ray and neutron spectroscopy. And here you can see a sample of a region of the moon and its gamma ray spectrum as taken from orbit. And this is from two different missions. One of them is Lunar Prospector with a BGO, so very poor resolution. And the other one is a Japanese mission, Kaguya, that had an HPG detector. So you can see the difference there. And here, this is from Lunar Prospector, the BGO detector, and the two helium-3 detectors. Those are neutron detectors. So more in depth, what is planetary nuclear spectroscopy? Well, it is a technique to measure the bulk elemental composition of surfaces of planetary objects. And by planetary objects, I mean, it can be a planet, it can be an asteroid, a comet, a moon. So as long as it's a solid surface, it's considered, we can use these spectrometers to measure the bulk elemental composition. So how do we do it? How does it work? It works by detecting gamma rays and neutrons that are being emitted from the surface of these objects. And as you know, gamma ray energies, they provide elemental identification, and their intensity can also provide quantification. So we can know how much of each element exists, as well as what the composition of the surface is made out of. Neutron detectors are particularly suited to detect hydrogen, as you know, because of large elastic cross in the proton neutron. Planetary nuclear spectrometers can be deployed on multiple platforms, and this is what is shown here. This is again Lunar Prospector. I'll be talking about it quite a bit because it's one of the most successful missions. And it's an orbiter that has a gamma ray spectrometer here and a neutron sensor there. And the advantages of having an orbital spectrometer is that you can map the entire surface of the planetary object, so you can get kilometer scale resolution. However, there are also landed spacecraft or rovers, and here's an example of a Curiosity rover that has an ET neutron generator for it. And the nuclear spectrometers aboard a lander, they give you a much finer resolution, so you get the composition right underneath the lander. And sometimes you can be more precise. You get high precision. So you might be wondering, where do these gamma rays and neutrons come from? And there are two answers to that question. The first is through galactic cosmic rays. That, as you can see, this is a representation of galactic cosmic rays that are penetrating through the surface. And these are high energy protons, and mostly protons and some helium ions that are emitted by the sun, and also they come all over. And through some escalation reactions, they liberate a bunch of neutrons that they rattle around, and mostly through inelastic scattering collisions and neutron capture, they excite the elements around the interaction point, and the de-excitation is followed by gamma rays. Some of these neutrons can also leak off the surface, and we can detect those. That is one part of the answer. The other part of the answer is that we can bring our own source of neutrons. So we can bring our own external excitation source in order to excite the nuclei underneath the surface. And that is mostly done with compact DT neutron generators. DT stands for deuterium and tritium. And they produce a monoenergetic 14 neutrons. And also there is natural radioactive elements that don't need an external source of excitation, and they emit those gamma rays that we can detect at the surface. So why do we do that? So there are many reasons, and a planetary scientist can probably answer this in more detail than me. But learning about the composition of planetary surfaces help us constrain our models and our theories of the formation and the evolutionary processes, not only of the object that we're investigating, but of the entire solar system. We can also identify resources. For example, we can identify Lunar Prospector was provided conclusive proof that there was water on the moon. So there is water in some cold traps or the permanently shadowed regions on the moon that had water ice. And Lunar Prospector, using gamma rays and mostly neutrons, was able to provide definitive proof that that was the case. Now, that is important because if we want to establish a permanent base on the moon, for example, we need to make use of the resources that are right there. Otherwise, it's impractical and very expensive. We can also identify anomalies, and I will show you later one example of that is called the Velkovich volcanic complex. That is one region on the far side of the moon that has a very different composition than the rest of it. And we still don't know why that is, but that was spotted with a gamma ray spectrometer. We can also detect biosignatures, and I'll talk about that in the context of Dragonfly. And biosignatures can be the detection of elements like carbon, hydrogen, nitrogen, oxygen, sulfur, or phosphorus. And they can provide an idea, or they can relay that information to other instruments. So they can go ahead and investigate further and see if there's some kind of prebiotic chemistry going on. There have been many missions that use nuclear spectrometers, meaning gamma rays and neutron spectrometers. And one thing worth noting here is that they go all the way back to the 60s and 70s, so the beginning of the space age. In the Apollo missions, they used neutron spectrometers, several asteroids like the 433 Eros and 4 Vesta and 1 Ceres. We were able to map also the northern latitudes of Mercury, the Messenger mission, and Lunar Prospector, of course. And the Mars Curiosity rover has a DT neutron generator located on the side. And it is the first and only so far that has an active gamma ray spectrometer. So it's a neutron spectrometer. It only has a neutron detector, it's not gamma. This is the kind of data that you can get from a gamma ray spectrometer. And this is again data from Lunar Prospector. And this is the thorium concentration on the near side of the moon and the far side of the moon. And here you can see this huge region that is very different in composition from the rest of the moon. This is the thorium concentration, and this is known as the kryptonite. And this is something that points to a different information process that we're still trying to figure out how it happened. This is the Velkovich volcanic complex that I was talking about. So the far side of the moon is more or less uniform, with the exception of some interesting anomalies that we're investigating why that is. Here on the other side of the screen, you can see plots of the gamma ray spectral data for the region that is immediately surrounding the Apollo landing sites. So these white dots are the Apollo landing sites. And here you can see the iron oxide composition, titanium oxide, thorium, and magnesium oxide. So this is just an example of an orbital gamma ray spectrometer and the kind of data we could get. So what kind of information do we get from neutrons? And as I mentioned before, they are uniquely suited to measure hydrogen composition. Suppression of epithermal neutrons specifically can tell you about hydrogen deposits. And here, this is one of the data sets from Lunar Prospector that shows clearly that in some of these regions where the sun doesn't reach, you have some water deposits there. Now, there are a lot of future missions also that are coming up that have either a gamma ray spectrometer, a neutron spectrometer, or both. A lot of emphasis is happening on the moon because of the Artemis program. And you can see that clearly here. But also an interesting one is asteroid Psyche, which is a metal-rich asteroid made of iron and nickel mostly. And it was believed to be a protoplanet that got smashed, and the core of that planet was exposed. Now that there's some doubts about whether or not that's the case, but we're going to go and investigate that anyways. And finally, there is the Dragonfly, which is a mission to Saturn's moon Titan. In this mission, there's going to be a nuclear-powered quadcopter that is going to fly around Titan, and it's going to cover about 200 kilometers in trip, more than any other rover previously. And what it's going to do is going to land at different locations, and it's going to take some important science data at every location. Now, it is equipped with a gamma ray and a Neutron spectrometer. But I'll talk a little bit about that later. First, let me give you an idea of how we're doing it, and then I'll explain a little bit why we're going to Titan. So Titan is, as you can see, is more or less the size of Mercury, but it has a very thick atmosphere. The atmosphere is about 50% higher than that of the Earth, but it's 1/7 of the gravity. And therefore, flying on Titan is actually it's very good. It's very easy to do. Generating lift is much easier. It's almost like swimming on Earth, not quite, but you get the point. And on Titan, you can see here, it's not a simulation, but it's a video of what we expect to do at Titan. This is a neutron generator that's illuminating the surface with neutrons, and that is the kind of data that we're going to get. So we're going to be able to map the hydrocarbons and the water composition of the lander. Now this is a skeleton of the quadcopter, and these are the scientific instruments. So we have DraGNS, which is a mass spectrometer, and it's going to look into prebiotic chemistry. So it's going to look into organic molecules as well as amino acids. Then we have DRACO, which is not a scientific instrument, but it's a drill that feeds the samples to DraGNS. Then we have DraGMet, which is the geophysics and meteorology package. And that's going to measure things like temperature, pressure, wind speed, seismic activity, and so on. We have DragonCam, which are the cameras, and it's going to relay all those images back to Earth. And finally, we have our instrument, which is DraGNS, a gamma ray and neutron spectrometer, has the better name. And it's composed of a pulse neutron generator here, a high purity germanium detector, and a helium-3 detector. So this is another way of taking advantage of the environment that you're in, because time is very cold, it's 90 Kelvin. So you don't need active cooling in the germanium crystal. You can just do it by passively cooling it in the Titan environment. So why Titan? And I think the simplest answer is because it's the only place outside of Earth that we know of that has complex organic chemistry going on. And this is very interesting because it can be thought of as a window to how Earth looked like 4 billion years ago, when organic molecules combine with liquid water, and the prebiotic chemistry is something that we want to understand. It's one of the biggest questions that NASA tries to answer. And the way that these organic molecules form is that there is photochemistry in the upper atmosphere that produces these complex organic molecules. And this is mostly due to energetic particles from Saturn and the Sun that form this PHS. And they kind of rain down on Titan, and then they cover the surface. And there's a potential for these organic compounds to have mixed with liquid water for an extended period of time on the surface. So DRAMS is uniquely suited, so the mass spectrometer, to look for these complex molecules. So Titan is a singular destination for understanding the chemical processes on Earth. That supported the development of life here on Earth about 4 billion years ago. And that is the main motivation. Because of the very thick atmosphere in Titan, we didn't really know how the surface looked like until there was a mission, the Cassini mission. That was around 2005. And in its belly, it had the Huygens probe. And Huygens, this is actual footage of Titan as the Huygens probe was landing on the surface of Titan. And what it saw, it was these large sand dunes that are made of organic material, as well as lakes and clouds and all those things but of course it's a methane cycle, not a liquid water cycle like we have in Earth. Now, talking a bit more about dragons. This is an MCMP simulation of more or less the footprint that you would get from the measurements. And this is a picture of one of the experiments that we did at Goddard with a water breaks and meteorites to see how fast we see nitrogen. Because that is one of the big science requirements that we have, the detection of nitrogen. And some of the science objectives here are to measure the composition of the building blocks of life, or the SNOP, all of these elements. That's sulfur, carbon, hydrogen, nitrogen, so on. Another question that we want to answer is there ammonia on the surface, which would suggest deposition as cryolava? And the answer would be yes, if we detect nitrogen with a concentration higher than 5% and carbon with concentration lower than 20%. Another question that we want to answer is, has the rocky core underneath Titan interacted with liquid water at some point? The answer would be yes, if we're able to detect sodium, potassium, magnesium at any level. And of course, there are more examples of those science objectives, and you're welcome to read the paper. Very interesting. Now, moving on to something more technical, there are challenges to gamma ray spectroscopy, as we know, and perhaps the limiting factor or the bottlenecks to getting a higher resolution, a higher precision, are the inconsistencies and gaps in gamma production cross-section microns. And in this audience, I don't have to define what a cross-section is, but here's the mathematical definition of it. And and by the way, the inelastic scattering cross-sections are particularly not good compared to captured cross-sections. So that is one area that we want to improve. And here's an example of an inelastic scattering cross-section on iron 56, which arguably is one of the best known cross-sections for inelastic scattering at 847 keV. And you can see agreement between many of the researchers. But on the other hand, this is an example of aluminum 27 Nm prime at 1720 keV. And you can see that not only that there's disagreement, but also there's a lack of data above 1200 years. So this is the kind of things that we want to improve. And of course, the effects of erroneous cross sections in our instruments result in inaccurate bulk composition, as you may imagine. This is an example of going back to the aluminum 27 cross section that I showed you, how our models MCMP underpredict the composition of fluid, for example. So therefore, with this in mind, a collaboration was established between NASA, APL, and LBL now in order to perform these precision inelastic scattering cross sections at 14 MeV, mostly for elements that are relevant to planetary nuclear spectroscopy. So what we proposed to use was a method known as associated particle imaging, which is for API for short. And the reason for that, I'll explain what API is, but I want to get to the objective first. And what API does is that it provides with absolute neutron flux measurements and position resolution. And this overcomes some of the main challenges in a state-of-the-art cross-section measurements. So as you know, maybe the gold standard of cross-section measurements is use a monitor photo or some standard that you know the cross-section relatively well. But of course, some of the problem is that you want to measure something relative to that, your error bars are never going to be better than the cross-section of the standard photo. Now, so API circumvents that by really having absolute neutron flux measurements. And the way that we do that is by detecting or by tagging each individual neutron. So here's an schematic of how API works. This is a DT neutron generator. This is the ion source where you have the deuterium and tritium ions, and they are accelerated towards a titanium target. And in that target, fusion reactions take place, and the product of that fusion reaction is an alpha particle and a neutron that are emitted back to back in the center mass frame. So by detecting these alpha particles, you can tag the individual neutrons. And then what you can do is you can count coincidences in the alpha detector and also on this neutron, then they can exit and interact in a sample that you want to investigate the image, and in a gamma ray is emitted. So by detecting this alpha particle and this gamma ray coincidence, you can effectively know when the neutron was emitted and the XY position. So, so that is the big advantage of the API. And Arun Perso is the PI at LBI. So we started our first measurement campaign in August of 2022. This is a CAD model of the API system up in building 58. And underneath is the API neutron column. So this whole setup that we have here, where we have our sample, it's a very thin iron foil, is traveling with, there are two gamma ray detectors, a lithium bromide detector and a bromide detector, and this whole setup fits underneath the API system here. And here you can see pictures of that setup basically. So we radiated high purity samples of iron, copper, and carbon. And this is just a snapshot of the results of iron. Of course, we wanted to do iron to have a proof of concept to see that this technique is actually doing what we wanted to do, and it's working as expected. And as I told you before, iron 56 is an ideal means to test this. So here we did. Here I'm just showing the analysis for the 846 kV line and the 1238 kV line, and this is our result compared to the other ones from different researchers. Same here, and you can see that it agrees very well. This is the same, just in table format. And these dotted lines here are from towers, which overpredict the cross section in both cases. So you can see that we were consistent with the results obtained previously, and we think we can get better errors than this. Here, the driver of the error right now is the efficiency calibration that we did with check sources that were good to within 5%. That was the decision. It was in 5%, 3%, and we can easily get our hands on check sources that have better precision than that. And that will automatically break down the errors in the cross section. So for the future work, in mid-February, we're going to begin the second round of measurements at LBL. We're going to do silicon, magnesium, oxygen, and nickel. A publication will follow. And we also established connections with the nuclear data group at LBL, Professor Bernstein here, and the National Nuclear Data Center at Brookhaven National Lab. So we hope to join forces and write a DOE proposal to create a database of 14 MeV cross sections similar to that of the Baghdad Atlas. And for some of you who don't know what Baghdad Atlas is probably the best database that we have so far of neutron inelastic scattering cross sections. And I use the paper with Professor Bernstein name here. And we use this database to predict the performance of our instruments all the time. However, as you know, the neutron flux is really it's typical of a fission reactor. So, and we're interested in higher energies than that. For Dragonfly specifically, we're interested in energies of 14 MeV and below. So, creating a similar atlas at 14 MeV can be very useful not only to us in the planetary nuclear spectroscopy community, but also to the nuclear physics community at large. And this is a secondary objective that we have. And this is an idea that came up after we got the proposal approved. And the idea is that we have already measured these elemental standards for the cross section, and therefore, through a simple linear combination of these standards, we can get the composition of a more complex sample, like a meteorite. So we radiated a piece of palisade, which is a stony iron meteorite. And we haven't finished the analysis or the rest of the standards, but simulations, MCMP simulations shows that after you take into account things like attenuation and so forth, that can be a very useful, that it works pretty much. And why would we want to do that? Because there is a critical need to have ground truth data to validate planetary nuclear spectrometers. So we have data out there of different asteroids, different moons, but we don't have bulk elemental composition of meteorites that are here on Earth. And the reason for that is that currently there are no instruments that can accurately measure the bulk composition of meteorites. I should clarify that because we have very sensitive instruments like mass spectrometers and highly precise, but they just take a point, for example, or just they measure the surface composition with X-ray spectrometers. But if you want to measure the bulk composition, you can see how heterogeneous the sample of a meteorite can be. So if you take a sample, what are the chances that you're going to get a representative composition? So there are currently no good and reliable methods to get the overall composition of the meteorite, and that is a very useful data point for classifying these different meteorites. So this is something that we are actively working on. And yeah, it's that's it. I want to bring your attention to some opportunities for graduate students that if they're interested in the Dragonfly mission, you can work for 2 years at 30% of the time at NASA, IPL, or others, depending on who your mentor is. And this is the link. There's also informal collaboration to test or continue developing a Python-based gamma spectroscopy GUI that I started during the pandemic. So you're welcome to check it out and collaborate, and you're always welcome to email me and comment. So with that, thank you. Ready to keep